did?
Yes.
Okay. Okay, good. So go ahead and also share your slides. I would like to see that your slides are also, it shows your slides.
On the slide?
You click on the cloud, right?
Yes.
Okay, sounds good.
Yes, it's actually.
I don't see your slides yet. Share content and share your stuff.
Is it good?
I don't see that. Yes, I see now. Okay, go first page. We start. All right. Hello, everybody. Today we have another guest speaker, Mujtaba Bishnezer. He is my PhD student here at Florida Atlantic University. Mujtaba is going to talk about lattice-based cryptography. So remember, we have discussed several key exchange mechanisms in the class, including ECC, RSA, and some other methods. Lattice-based crypto is another method, which is one of the strong candidates against attacks of quantum computers. So Mujtaba will introduce lattice-based cryptography, and he will narrow down his the topic, and he will provide all kind of performance numbers and an example at the end. If you have any question, please feel free to ask interactive, and he'll be able to answer your questions. Mujtaba, with that, I will let you know to start, and we go from there.
Thank you so much. Hello, everyone. Welcome to my presentation. I'm Mujtaba Bishnezer. I actually will present you the lattice-based cryptography and introduce, actually, I try to introduce you what is the lattice, what is the hard problem here, how we can actually generate a post-quantum actually crypto system. And then we narrowed down to actually Kyber, which is one of the finalists, as Dr. Rezo said, is actually a strong candidate in the latest round of the NIST competition. So we try actually to introduce it and introduce some specific actually features of this crypto system. In this presentation, we have actually at first some introduction about the public key cryptography. Then we actually speak about the lattices and different features of the lattice. Then we have actually have some sage codes, an example for key generation, for actually generating the shared secret key between two parties during through the unsecure channels such as the internet. We have actually a sage code here. We can actually go step by step with each other to understand how we can actually create that key. Then we actually have some slides about the Kyber specifications and its performance comparison with other actually systems, crypto systems. If you have any question, you can actually ask during the this presentation whenever you want. It's okay, and I try actually to answer you my best. Okay, you know actually the importance of the public key cryptography. Public key cryptography is one of the most actually important tool for communication through unsecure channel, as I said. We want actually two parties, actually Alice and Bob, want to talk to each other, communicate to each other. They have some actually symmetric primitives such as the AES, so they need to share secret key for actually encrypt and decrypt their messages using actually the AES. So public key cryptography is a tool which they use to actually share the shared secret key, and it's one of the actually most important, as I said, tool in the cryptography system. the current actually system, the current crypto system are based on the two main problems: the factoring large integers and actually logarithm problem. For example, RSA, as you actually reviewed during this course, is a crypto system which you need to choose two very large actually integers and compute the multiplication between them. So if the result is given, you can't actually break the security of RSA because you can't actually factorize that number, and because actually the factorization of that large number is known as actually a hard problem, and we can't actually solve by our current actually system, our current computers. For the ECC, we have the same story. In the ECC, as you know, and as you studied during this course, we choose a generator, then we compute actually exponential of actually g power of a very large number. So having that result, you can actually find that key which is used in the actually exponential in the actually the g power of actually that number, the key. Finding the key is known as a hard problem because actually you need to compute the discrete logarithm, which is very hard actually problem for our current system. But this problem actually can be solved by the quantum computers. It is shown by Shor that this problem, although they are actually they are very hard for our current actually computers, but quantum actually the quantum computer will be break them, can factorize that large number, can compute the discrete logarithm for that large number. So we need to provide actually a new crypto system which is resist against actually the computation power of the quantum computers actually. So the NIST actually has started several years ago a competition for providing a new types of the crypto system, which is known as a post-quantum cryptography. And these types of actually crypto system can be resist attacks using classical and quantum computers. We have actually different approach for these types of crypto system. There were different candidates during the round 1 and round 2 of these competitions, and as you know, there are different approaches based on the lattice-based crypto, code-based crypto, isogeny-based crypto, and actually some more actually systems. Different actually in this actually types of the approach has each of them has actually a specific actually mathematical background, has some specific actually features, but we try actually to focus on the lattice-based crypto because, for example, in the round 2, between 26 candidates, there are 17 actually candidates based on the lattice-based, which means the importance of actually this approach compared to other. So we need actually study more about it in this presentation. And here, recently, as you see, NIST actually announced the finalists in the round 3. There are 4 different actually schemes for public key and 3 actually schemes for digital signatures, as you see here. And there are actually some other actually approach known as alternative candidates, such as BIKE for the claim, HQC, Enterprime, or site. If in actually the in the actually third round. However, it seems that one of actually this approach will be selected. Between this approach, there are three lattice-based crypto systems. Crystal, Kyber, Entro, and Saber are based on the lattice-based, which again actually shows the importance of actually lattice-based cryptography. And I should say that Crystal Kyber here has some specific features. It actually shared a common framework with the Crystal Lithium, which is another scheme for the digital signature. Is based on the actually modular lattice-based actually modular LWR problem, which I actually will introduce you in later slide. And it has a very actually good performance compared to other even our current actually crypto systems such as the ECC, and we can actually use this crypto system in even actually very low actually cost or limited actually resources devices such as IoT devices. They have only actually limited, as you know, resources. They have very limited area. They have very low computational power. So Kyber has very actually compact architecture, has very high performance actually features that can be used for them for providing a post-quantum actually crypto system, as I said, even on the IoT devices. So now we want actually introduce the lattice. What is the lattice? Lattice actually is a linear combination of independent actually vectors Bi. You need actually to define some vectors, some bases. Then any actually linear combination of them will be actually a point on this lattice. For example, if n is equal to 2, you can actually choose two vectors b1 and b2 as your basis. For example, b1 is equal to 4 and 2, and b2 is equal to -3 and 4. So any actual linear combination of them when z1 and z2 are actually integers can be actually results in a point on the lattice. Can you actually tell me some points on this lattice? Suppose that z1 and z2 is an integer number. For example, z1 is equal to 0 and z2 is equal to 0. So we can actually compute the z1 b1 plus z2 b2, which will be 0 and 0. If z1 is equal to 1 and z2 is equal to 0, the linear combination of z1 b1 plus z2 b2 will be 4 and 2, which is another point on this lattice. If z1 is equal to 0, z2 is equal to 1, the result will be -3 and 4, which is another point on this lattice. And for z1 and z2 both equal to 1, the result will be 1 and 6. This is another point on this lattice. So if we want actually to draw our lattice based on this actually basis, we have these points. This is our 0, 0 point. This is our 4 and 2 point. This is another point, which is -3 and 4. And these two blue vectors are actually bases. These are B1, 4 and 2, and this is actually our B2, -3 and 4. And as you see, we have different points here, which can be actually calculated by a linear combination of B1 and B2 to actually create our lattice. For example, this point is can be actually computed by addition of B1 plus B2. This point is inverse of the B1. This point is inverse of the B2. Any actual combination will result in actually a point on our lattice. Now we want to actually show different actually lattice based on different bases. Here we can actually define our first actual lattice bases, x1 and x2, x1 and y1, and x2 and y2 is our second actual basis. So you can actually draw this software can actually draw your lattice based on this basis. For example, we change it to another point. And this is our new basis, new actual points, new our lattice tree. And you can actually see here the point on our actual lattices. 2 and 1, 2 and 3, 2 and 5, 2 and 4 and 7. And all actual points, not all points, but some example point on actually our lattices. Here we have some other example. For example, if x1 and x2 will be 53 and -19, and x2 and y2 will be 25 and 6, our lattice will be such as this actually shape. All points here is our lattice grid. It's very actually easy concept. If I actually introduce in as a 1001, it will be like our Cartesian actually points. That's it. Okay. Now, what is actually the hard problem here? The lattice, as we see, it's very actually easy concept. So what is actually the hard problem here? One of the hard problem here is SVP or SVP is the closest actually vector problem. Two actually vector is given for B1 and B2. For this example, we have 5, 1 for the first actually basis and -2 and 8 for the second basis. So we want actually to draw our actually lattice grid. And these actually vectors are our actually basis vector. As you see, the degree between these bases are near to 90 degrees. We call them orthogonal. So it is shown that if your vectors have the degree of almost 90 degrees, you can actually solve this problem easily. Here, suppose that we want actually to find the nearest point near to this specific point, 27 and 8, when your B1 and B2 is 5, 1 and -2 and 8. For finding actually the nearest point to this specific point, we actually create our multivariable linear equation here and try to find the Z1 and Z2 based on these equations. Z1 and Z2 will be equal to these numbers, but this actually, as we know, Z1 and Z2 should be an integer, should be actually the integer numbers, so we need to round them. So Z1 will be rounded to 6 and Z2 will be rounded to 0. If we actually compute the point using this actually value of Z1 and Z2, the result will be 6 multiple 5 plus 0 multiple -2 equal to 30, and 6 multiple 1 plus 0 multiple 8 equal to 6. The point here, 30 and 6, will be actually the nearest, is actually the nearest point on our lattice near to this specific point. We can't find actually this point, as I said, because the degree of our between our bases is almost 90 degrees. If actually the result, if the angle between them will be near to close, this problem actually will be changed to a very hard problem. Suppose that our bases will are actually 37 and 41 for B1 and 103 and 113 for B2. Our new actually vectors, our new bases can be drawn by this figure, as you see, and it's very actually easy to see that these vectors are very close to each other. They are almost parallel, not parallel, but the actually angle between them is nearly 0. Now, actually, if you want again find the nearest point to this specific point, we need again actually define our multivariable linear equation, linear actually system, and find the value of Z1 and Z2. The Z1 is equal to minus 53 point something, and Z2 will be actually 19.3. Again, we need actually to round them because Z1 and Z2 should be actually the integer number. So the result will be minus 53 and 19. The point actually using this actually value of Z1 and Z2 will be minus 4 and minus 26. But this number is not close to this actually a specific point. For example, I can actually, as you know, this point is another point in our lattice using the value of Z1 equal to 1 and Z2 equal to 0 for Z1 and Z2. So this point is more closer to this point compared to this point. It's very obvious. Therefore, if the result between the base, if the angle between the bases is near to 0, we find this actually solving the CVP problem or SVP is too hard. Therefore, it makes our actually system a quantum safe actually crypto system. You can use it to generate, to actually build the approach, build the actually crypto system to which can actually resist against actually the quantum computers. We have some actually other example for this approach, you can actually define our different vectors, different actually bases for x1 and y1 for b1, and x2 and y2 for b2, and define a specific point. For example, in our example, for the first example, was y1, okay, and the point is 27 and 8. This is our actually desirable point, and this is our basis. So here, as you see, the nearest point is computed as a 13 and 6. Here we have the same result. If we change it to this actually basis, for example, 37, 41, 103, 118. For the same actually point, the result will be -4, -26. Here, actually, the angle between the vectors is shown by theta, cosine theta, as you see here. If it's near to 1, it means that the result is not trustable. You can't actually trust this result because, as we see here, if our bases will be very close to each other, we can't actually solve the nearest point problem. As you see here, the difficulty of our actually problem or lattice is based on actually the shape of the bases. So when we have two, as you see, you have two different types of the shapes, the good set of the BI, for example, and the bad shape of actually the BI. The good shape of the BI, they are actually almost the degree between them is 90 degrees. So you can solve this actually lattice. You can solve the problem based on this lattice. And the security of this actually crypto system will be broken easily. While for this actually basis, when we define it over the same actually lattice, they are very actually these bases are near to each other, so it results in actually a hard problem, and we named it, we called it the bad basis. Any questions so far? Okay. We have different actually problem based on the lattice. The SVP, as I said, is one of actually the problem when you have the lattice base and lattice actually basis B, and you need to find the shortest non-zero vector for actually our given lattice. For the actually, there are another actually different, as I said, problem. BDD is another actually hard problem. When you have B, when you have actually the T is given, is a vector, and the parameter alpha is given. So you are asked to find actually vector V is closest to actually T. This is another actually hard problem based on the lattice, but we don't want actually to go details of them for this presentation. Now the question is how we can guarantee that our basis is in the bad shape. How we can guarantee the problem, the hardness of the problem. one of actually the approach that guarantee that your bases can be actually provide a very actually resistant crypto system is learning with error. In learning actually with error or LWE can provide actually a hard a hard problem, can provide a resistant crypto system, and actually guarantees that can guarantee that your bases are in the bad shapes. So we want actually to introduce this method. In the learning with error, the matrix of A is given, which is a uniform actually random number, and a noise actual distribution is given. So the AS plus E, this equation, the result of this equation is given also when E is actually sampled from the noise distribution. So there are two actually different hard problem here, different version of actually the hard problem. The search version is you are asked for finding the S. You have actually the result of AS plus E. You have the value of A, and you are asked actually to find the S. This is the equation AS plus B equal to T, for example. You have these blue actually values, and you're asked to find actually these green vectors S. Another version is decision version, when you're asked for actually distinguish between LW samples from a uniform random number. So there are actually the same actually problem, a different version of the same problem. As you know, if the equation is AS plus T, the computation of S is very easy. You need only compute the inverse of A, then S can be computed by inverse of A multiplied by T. It has actually, you need to only create a equation system for the value of S, and then find each value of S based on actually these equations. But when you have, when you add actually E to the result here, you change the value of T. So as you see here, the number of variables are more than the number of equations. So finding the S value will be so hard. This is actually the best approach for this approach actually is named learning with error. So you actually add error to A multiplied by S to guarantee that your problem is a hard problem. For example, here, if the A, the first row is 4, 1, 11, and 10, then you multiply actually this row to this column, which is S. S here is the secret key. If you actually multiply this value to this value and add them, 4 by 6 plus 1 by 9 plus 11 by 11 plus 10 by 11, and you actually all this, I should mention that all these actually operations here is in the finite field domain, so you need actually reduced in respect to value of Q. Q here is 13. If you compute actually this equation, then you have 4 here. So if you have actually this blue values, finding these numbers for S is so easy for this actually equation. by inversing of the A and multiplication and computing the multiplication between the inverse of this matrix by this vector, while when you add this error with very small coefficients, as you see, the coefficients of E is between -1 and 1. So you change actually the value of T, and finding S here will be a hard problem. Any question? Why actually this equation is so hard? Actually, suppose this is actually another sample of the learning with error. You have a by n by n dimensions, and you have a long actually E, and then the result is T. Here again, the number of actually variables are more than the number of equations. So you need actually try different values for E to find actually the appropriate, the correct actually E, to actually find the value of E here. For this actual sample, suppose that E has again very small coefficients. So we actually suppose that the coefficients of E is equal to 0 or 1, which is fully binary. So for this actually problem, we have 2 power of n different status for E. For the first coefficient, it can be 0 or 1. For the second one, it's the same until the last. So you have 2 power of n different actually status for E, and you need actually to test it to find the value of to find actually E based on the given A and T, which is not a easy actually problem when the number of M is too long. The best algorithm, as you see here, needs 2 power of n to actually find the value of E here. So the learning with error can be known as a difficult problem and is used in different post-quantum crypto systems. Again, I actually show you the value of the equation of the linear learning with error. Actually, LWE equation here is shown again here. This is actually the coefficients of A. This is the coefficients of S. This is our secret key. This is the coefficients of E and the result. As you see, for saving actually this matrix, which is our public key, we need n power of 2 actually storage. So we need, as you see, the storing of this matrix needs a huge actually amount of memory if n is too large. It's not actually, I should actually correct my sentence. It's not too actually large memory compared to our current actually file size, but compared to our actually current crypto system, is too large actually. And the computation cost between multiplication between this matrix and this vector is n power of 2 again, because actually the cost of addition is very actually can be ignored compared to cost of the multiplication. multiplication, we set here only the cost of equation equal to cost of the multiplication. So as you see, we need n power of 2 actually storage place and n power of 2 computation, which means that learning with errors is a very costly actually approach. For actually some IoT devices, when actually they have very limited resources, very limited power, they have limited battery, they have limited computation power. So actually storing this amount of value or computing this amount of actually multiplication is too large. So there are some other methods to reduce this cost, which is known as a Ring-LWR. Ring-LWR or ring learning with errors is another approach which reduces the cost of the storage to n and the cost of computation by n log n. For this approach, actually, we have the first column equal to A00, A10, A20 until A9 and N. Then suppose actually this column is a polynomial, then you can actually, for example, you can write it as a, you can write here, okay. It is actually A0 plus A1x plus A2x power of 2 and so on, n actually multiplied by x power of n minus 1. So then if you multiply this polynomial by x and then reduce it respect to actually ring equation, you have A0, it's actually equal to shifting all coefficients by 1 downward, and then the last one will be entered as a first actually coefficient with actually minus here. So the A0 will be changed here, A1 will be placed here, A3 here, and so on, and the last one in n will be actually converted to minus an and will be entered as a first coefficient in the second row, second column, excuse me. And we can actually create all actually our matrix based on the first column. It means that if you can store the first column, you can actually create all your matrix by it. Then you can actually reduce the storage cost. Again, for the computation, you have, as you see, we have actually some relation between the first and the second actually columns. The second columns is actually can be write as a x multiple that the first polynomial. So we can actually use some approach here to reduce the cost of the computation from n power of 2 to n log n. This actually approach called here entity, which is another actually types of FFT, as you actually learned it in your previous courses, and can be applied to here. We don't want to actually go details about it, but as you see here, we can reduce the computation cost here. For example, suppose n is equal to 256. Therefore, using this approach, Ring-LWE can reduce almost 98% of actually computation cost compared to original actually approach LWE. It is at 256 power of 2 and here it will be 256 multiplied by 8, which results in 98 actually percent of reduction, computation reduction. For the storage, we have the same story. Reduce actually the huge amount of actually capacity, storage capacity, to only storing one column. That's it. It's very actually efficient approach which used in different crypto systems such as the Kyber. Kyber actually use Ring-LWE. Excuse me. Kyber use actually this approach for providing a post-quantum crypto systems. Again, we can actually increase the hardness of our problem by using repeating our polynomial. For example, if our vectors have some another dimension such as depths, you can actually have, for example, if chi is equal to 2, you have 4 A matrix here. Here we have only one actually matrix of A. For k equal to 2, we have 4 different actually matrix of A here, and 2 vectors of S, 2 vectors of E, and 2 vectors of T. Then we need a store actually k power of 2 by n different actually columns. For example, as I said, if k is equal to 2, you need only store 4 actually columns of these vectors. The first column of this vector, the first column of this vector, the first of this, and first of actually these vectors, this vector, and you can actually build our actually matrix with these only 4 columns. Then you have compute actually this equation as plus e by k power of 2 by n log n computation cost. So for the Kyber, as we will see in the actually other slides, the next slides, for increasing the security level of the crypto system, it increases the value of k. For example, for the first security level, k is equal to 2. For the next security level, the k will be increased to the 3. So for the next actually security level, k can be actually increased to the 4. If k is equal to 4, we have 16 different matrices of A here, and we have 4 different actually vectors of S. We can actually use vector or polynomial here. They are the same actually concept here, because each vector can be known as a polynomial by degree of n. So as I said, 16 actually matrix of A and 4 actually polynomials of S, 4 polynomials of E, and the result will be 4 polynomials here for T. This is very actually practical approach for our current actually candidates in the NIST competition. Any questions so far? Okay, again, we want actually review what we actually learned so far. We know what is the lattice. Lattice is a linear combination of some actually bases. We choose some bases. For example, in our example, we choose two actually bases. Here, and then we actually create our lattices based on these actually vectors. This is our first basis, this is our second basis. We actually define our lattice grids based on them. And then we actually define the closest vector problem, which is actually the hardness of the lattice-based crypto system is based on actually such as this problem. We define that in some cases, this problem is too hard and cannot be cannot be solved by the quantum computers. And we know that this hardness is based on actually the shape of the bases. Therefore, we actually define a method, linear with errors method, which guarantees that our lattice spaces is in the bad shapes, and our problem will be a hard problem. Then we actually try to reduce the cost of storage and the cost of computations in linear with errors method, because it needs a lot of actually storage and computation cost. And we actually introduced the RLWE method and modulo actually LWE method for reducing the cost of the storage and computation and increase the security of the crypto system based on actually our based on what we want. If we want, for example, increasing the security, we need to increase the K in this equation here. Now we want to actually practice how two parties, Alice and Bob, can communicate to each other using actually the lattice-based cryptography. And then we actually try to solve an example with the stage code to understand what's going on in actually lattice-based cryptography. Again, for example, RSA and ECC approach, each parties use, we know that each parties use another actually public key of other party to generate the shared secret key. And then they compute their actually, at first they compute their public key, their own key. Then they actually publish their own key for others. Then others, for example, Bob use the Alice actually public key to compute actually his compute the shared secret key, and then Alice again actually uses the Bob's public key to compute actually her own shared secret key, not own the shared secret key actually, and the shared secret key between them will be the same, and they use actually that key for communication through the, for example, using actually the symmetric crypto actually primitives such as the AES to communicate with each other. Here we have actually another encryption method. It works the same, but has actually some differences. Here, actually, Alice computes this equation that we known as a LW actually E method, AS plus E equal to T. He choose actually A from a uniform random number, and he choose actually E from a noise actually a noise actually distribution, and S is the same from actually can be choose from the noise distribution. For all actually methods, doesn't matter. E should be actually has very small coefficients. We use actually this feature in our computations. So she computes actually this equation and publish her own public key, which is A, and the result of this equation, which is T. So A and T will be published by Alice, and S will be kept, which is the secret key, and no one actually knows about the value of this vector. Bob, on the other side, actually receives the value of A and T, and he tries to compute this equation using a random number of R. He chooses some actually random number which is secret for the vector of R, and compute and then he computes R multiplied by A plus E1. E1 and E2 are actually the again the noise actual distribution. They are sampled from the noise distribution. They have again actually a small coefficients, and he computes the value of U and V, which is shown by red here. So U is computed by R multiplied by A plus E1 and plus 0, which you can ignore it, which is U. And V is computed by R multiplied by T plus E2 plus M. M here is actually a shared secret key. So Bob choose a shared secret key, choose a key here, and try to encrypt it using the U and V, which is called cybertext. And Alice again receive the U and V from actually Alice actually receives the U and V from Bob and try actually to find the value of M. So again, the secret key here is the M. Not the secret key, the shared secret key actually, because each party has own actually secret key. For example, Alice secret key is S, but the shared secret key, which is used in the AES, for example, crypto system, is M. Now I want to rearrange this equation to find the actually relation between U, V, and M. The V can be again actually write actually as a RT plus E2 plus M. And if you actually again see this figure, R multiplied by T plus E2 plus M is equal to V. Then we actually rearrange this equation, and as actually you know, T can be derived as a AS plus E, because we know that we don't know the value of S and E, but we know that T can be computed by AS plus E. Therefore, we can actually place this equation instead of t here, and the result will be RA multiplied by S for the first term. For the second term, R will be multiplied by actually E, which is which actually has small coefficients. So the result will be very small coefficients, which is shown here by yellow box, plus E2. E2 again has is actually a small coefficients. It's actually a noise. So we can ignore the multiplication between a big number with a very small number, not big number, and the value of multiplication of the vector with very small actually numbers can be ignored, which is shown here by this yellow box. And this actually equation will be added by m, which is our shared secret key. So m can be derived as a RAS plus a small value here plus n. Is it clear? We only actually rearrange this equation. Here I actually write these equations near each other, but as you see, we have two equations here. One of them, the right side, we have for v. For the left side, we have for v. Another equation for u. U and v are our ciphertext. M is actually the message, is our shared secret key. And E1, E2, E here, the yellow actually boxes have actually their small coefficients. They are sampled from the noise distribution. In our actually example, their coefficients are between -1, for example, to 1. And A and T is actually extracted from the Alice public key, as you see here. Then we rewrite again the equation for V, and we reach this equation, which is RA plus S plus RAS plus a small actually value plus n. Again, if we actually compute the value of US, when U is our ciphertext here, and can be written as RA plus E1. We have 0 here, we can ignore it. We rewrite actually the value of U as RA plus E1. And if we compute it, if we actually multiply this value by S, we have RA multiplied by S plus, again, the value of E1, the product of E1 by S is a small actually value, can be known as a noise, and we show this value by this yellow box. Here, this value RAS is equal to V minus M. We compute the value of V, which is here. So V minus M is RAS plus a small value. So we have actually again something like this here. The difference between this actual equation and the previous equation is these two yellow boxes that we don't know actually the exact value of them, but we know that they are very small. They are actually such a noise. So we can say that US is almost equal to V minus M. So actually easy and straightforward computation. Okay, so if we compute V minus US, because we know that US is equal to, as we said here, US is equal to, almost equal to V minus M. If you compute V minus US, the result will be M plus a small value here. Therefore, we can actually decrypt the message of M, decrypt actually the shared secret key of M using actually the V and U. Not also actually Alice. Alice decrypts the V and U by her own actually shared secret key, by her own actually secret key S, and can actually extract the value of M. Then both parties, Alice and Bob, have the same actually value of M and can use it as a shared circuit key for feeding the AES to communicate each other through the for example, internet. Here we have actually an example, the sage example. We can talk about it. We have some parameters. I won't actually show them to you live, but at first I describe some features in this actually example, and then we can actually through it live and there's some different actually. We have some actual parameters, the n, the k, and the q. N is actually the degree of the polynomials. It is actually is not true. N is 4 and k is 1. My mistake. Excuse me. And Alice actually, the first party, choose the value of a randomly. We choose it here. This is our a. A is the n by n three matrix, which is the 4 by 4 here. It has 16 actually different values. She chooses actually her own secret key S. It is actually 6, 9, 11, and 11. And she chooses actually the value of E with very small actually coefficients from noise distribution, which is 0, -1, 1, and 1. Then in key generation, she computes actually the multiplication between A and S, and then the result will be added by E. So she computes this actually results as her own actually public key. A and T are actually the Alice public key. Then Bob, the other side, received actually the A and T. He chooses her own random number, which is this vector. He chooses actually the value of E1 and E2, and the secret key of actually m, which is here, for example, this number. Then actually he computes the RA plus E1 for U, and the value of U will be computed, and then computes RT, multiplication between matrix R and T, and he adds the value of E2 and M to the result, and this will be the final result of the encryption for V. So U and V, which are the ciphertexts, will be published, will be sent to actually Alice again. Alice uses actually the value of U with their own actually secret key, compute U multiplied by S, and then he subtract the value of V minus the result, and the result here of 2 is the value actually of the message. We check that this recovered value is equal to the message, which is true. It will be actually example for your actually question in your exam. We again try actually to compute it with different value. Here n is 4, k is 1, and q is 13. What is the n? N is the degree of A, the number of actually rows and columns of A, and it is actually the number of rows of A, S, the number of rows of E, and the number of rows of T. And show this is N. What is the K? K is the number of columns here. This is the number of columns here. We have actually the same slide here for increasing the number of K, but suppose for actually, because we want to work on the simple example, we suppose that K here is equal to 1. So we have only one matrix of A, one actually polynomial of S, one polynomial of E, and one polynomial of T will be the result. Okay, we choose randomly the value of A, or A. Then we have actually the same numbers here, 4, 1, 11, 10 for the first row, and so on. Then we choose actually the random number for S, for Alice. All these actually equation here will be computed in the Alice side. Alice actually computes them. She chooses the value of S. She chooses the value of E with small coefficients. Then she computes this equation. This is the this computation will be performed by Alice. It's very actually easy equation, multiplication between A and S. As you see here, we have actually a matrix multiplication, which is reduced by Q. Q is our actually prime number, and all numbers should be reduced by this. All operations should be actually performed by actually over this actually number, and we have actually modular, such as the ECCN RSA. We have modular addition, modular multiplication, modular actually subtraction, and modular inversion here, which is actually defined over the polynomial rings. So we compute the matrix by matrix multiplication reduced by Q, which is our actually prime number, equal to 13. Then the result actually will be added by E, which is our error, and this is our E, and the result actually is 47211, such as this estimate. Then the value of A and value of T is actually transferred to Bob actually, and Bob actually receives them. So encryption is actually will be performed by Bob. He chooses a random number. The E1 and E2 here should be as the a small number. Then we actually compute the Q. U, as you see here, can be computed by RA plus E1. R is actually a vector, row vector. A is a matrix, therefore the result will be a vector. Then the result will be added by E1, then it will be equal to U. We compute actually R multiplied by A. The direction of multiplication here is important. As you know, when we have actually matrix and vector, the direction of actual multiplication is important. For example, A multiplied by R is not, for this example, cannot be done because actually the number of actually columns of the first term should be equal to the number of the rows of the second term of the multiplication. So here the result will be added by E1, and this is actually the result here. The result actually should change because I changed some values here. The value of V can be computed by multiplication between R and T. R by T, when we have 1 by, for example, 4 here, and the vector of T is 4 by 1, the result will be Y matrix of Y by 1. So the result of V will be 12, which is in each actually step of computation, we reduce the result respect to the Q, as you see. It's very actually easy computation. We add the matrix to each other and reduce it by Q. Then in the decryption, again, Alice received the value of U and V. She computes actually the value of F1 and F2. And then we should actually add some things here. The value of F2, the second I show you the value of F2. The value of F2 here is 10. Okay. The value of M that Bob chose is 1. The value of M should be equal to 0 or 1 for encrypting only one bit. Here, if the value of F2 is equal to, is actually bigger than Q multiplied by 2, the result should be changed to the 1. This is actually a step that I forgot to write it before. If actually the decrypted message F2 is bigger than the half of the Q, which is 13 multiplied by 2, we assume that the result is 1. The F2 is 1. And if it's actually lower than this value, it is 0. Why this F2 is 10 is differ from actually the value of M. We choose M here equal to 1. Because as you see here, the value of our actually our decryption is equal to M plus something. We don't know the value of this something, but we know that this is ignorable. We ignore this actually value by rounding the result. If we choose M between 0 and 1, we can actually round the result to the 0 when the result is lower than Q multiplied by 2, and we can actually round it to the 1 if the result is bigger than half. If it's bigger than half, we can actually round it to the 1. If it's actually lower than half, we round it to the 0. It's very actually easy computation. And by this actually step, we can ignore the this yellow box. We can ignore the effect of this actually adding noise to our computation. We use this actually noise to convert to actually enhance our computation, our normal computation, to a post-quantum or quantum safe computation. And we can ignore, we can actually cancel actually its effect by rounding the result. But as you see here, for encrypting only one bit here, we need a lot of actually amount of A. For example, for our result, we need n power of 2 actually samples for A. We have k samples for S, we have k samples for T, we have n power of 2 computation here. We have actually, we should transfer n by n power of 2 plus n by k actually data from Alice to Bob. Bob should compute all these computations for only encrypting 1 bit here, and he computes the U and V when U has k by n dimension and the V has k by k power of 2. Then again we should transfer this cybertext to Alice, which has k by n plus k actually bits, and again Alice should compute this equation to decrypt only 1 bit. It means that we need a lot of actual amounts of data transmission, excuse me, for between Alice and Bob during this communication for encrypting only 1 bit. Any question? So, as you see here, for the Kyber crypto system, we have different key security level. NIST actually announced some requirements for different security levels entitled 1, 3, and 5. Kyber 512 is proposed for NIST security level of 1, which the N in this actually crypto system has 256 actually coefficients. It means the degree of the polynomials, for example, each S in our equation has 256 coefficients. A in our coefficients has actually n by n actually coefficients, as we see. And it used actually the k equal to 2 as again we as you remember we should repeat the value of n, not repeat. We should actually have different a here for computing this equation. So for the Kyber 512, we have k equal to 2. It means that we have 4 different matrices. We have 2 polynomials of degree 256 for S0 and S1. We have 2 actually polynomial of degree 256 for E0 and E1, and the result will be 2 actually polynomial of degree 256 for T0 and T1. And for this actually crypto system, the Q is equal to 3329, which is a prime number. And as you see here, the size of the secret key, the size of the public key, and the size of the cybertext, which is U plus E, is actually reported actually in bytes. We need actually 1632 actually bytes for secret key for security level 1, while the public key needs 800 bytes, and cybertext will be actually 768 bytes. as you see, the number of actually the size of the keys here is too higher, is too much compared to other actually our current crypto systems such as the ECC, but it can guarantee that our computation is quantum safe. For increasing the security, we increase the degree of the K. As you see here, the degree of the polynomial are the same for is the same actually for all these approaches, but K is increased. So for example, the last one, the A in our actual crypto system needs to is actually includes of 4x4 matrix of actually n by n, which is a huge actual number of the number here. So the size again increases, as you see, which is too much compared to our actually ECC, for example, approach in the pre-quantum computing, excuse me, or compared to our actually classical actually systems, or even compared to some specific actually ECC-based post-quantum approach called PSYCH in the NIST actually alternative candidates in the round 3. The size of the actually keys in that approach is too smaller, is very compact compared to other approaches. However, it needs more computation time. Here we have actually these numbers for the computing the for the lattice-based cryptography for Kyber crypto system, and then we can actually compare the amount of the cycles, the amount of actual time for this computation. As you see, the RSA, the curve 25519, and Kyber actually are compared to each other. The two first one are the pre-quantum, while the last one, the Kyber, is the post-quantum approach. As you see, the ECC, the curve 25119 is an ECC actually example, while the first one is the RSA approach. It's obvious. And the last one is actually the lattice-based post-quantum key encapsulation mechanism. We want to actually compare the size of the actually keys here. SK means secret key, PK means public key, and CT means ciphertext size. Actually the curve 25119, the ECC approach, we actually bring here the number of the cycles, the performance results, its performance results for the key actually exchange approach for the elliptic curve Diffie-Hellman key exchange approach, which needs this amount of cycles, and it actually provide this number of the size for secret key and public key. While, as you see, the RSA needs a lot of actually computation power, and the number of the actually public key and ciphertext size in key encapsulation mechanism for encapsulation and decapsulation actually approach is not too much. It's only 256 actual bytes. Although the ECC is more compact, but this number is not too much compared to, for example, Kyber approach in the lattice-based. Most of actually lattice-based approach has the same, not the same, but in the same order of the actually size of the number. And as you see here, we need actually the ECC, as you know, is is more efficient than RSA, using a very actually compact and efficient architectures. It can be used for IoT devices, for different actually systems. Most actually websites now use actually this curve, because as you know, we talk about the post-quantum, but it's not actually standardized yet. So most of actually governmental actually organizations use the ECC. It's actually very efficient, but as you know, it will be break. It can be actually broken by quantum computers. So as you see, the performance actually results for the Kyber at the end line. Alice and Bob try actually to generate a shared secret key between them through the encapsulation and decapsulations actually functions. As you see, the number of cycles, the actually cycle counts here is not too much. It's very actually efficient. It can be done in very actually the compact actually architecture. It can be done in very fast, and even actually compared to the pre-quantum systems, it can be actually applicable for IoT devices. It can be applicable. It can be used for actually our different actually systems in different actually performance level. We can use it in the actually IoT devices, in the high performance devices. However, the most important actually things here is compared to, if I want to compare actually the lattice-based crypto to, for example, Curve 25118, it needs actually more time for transmission of the its keys, its public key and the cybertext here. It needs more time. It's not a big deal because, as you know, for example, here the transmission can be actually can be done efficiently, and it's not a very actually big problem. However, if we have some issue here, actually we should work with other approaches, such as, for example, as I explained to you, with Ring-LWE, which is used in Kyber, or modular LWE, which can compact more our actually lattice-based crypto system. And as you see, the performance is considerable and shows a good performance compared to other approaches. Thanks for actually having me, and if you have any question, please let me know. I try to answer you. In this actually presentation, we thank you, Emrah. In this presentation, we actually have some actually introduction for the importance of the public key cryptography. Then we define different quantum safe approaches in the actually for providing the quantum safe crypto system. Then we reviewed the NIST results, and the NIST finalists and alternative candidates in the round 3. And then we have some overview for the lattice-based cryptography and the importance of the lattice-based cryptography between these candidates. As you know, we have 3 lattice-based crypto systems between the finalists here. We have some basic introduction of the lattices, which is it is a linear combination of the independent vectors. We introduce the bases, we introduce the actual lattice grids, we define the hard problem over the lattice-based scheme. We know that the vector problem, the closest vector problem can be solved in some conditions, but can be known as a hard problem in some certain conditions when the angle of the basis is too much close, it is too much lethal near the 0. Then we speak about the good shape of bases and bad shape of bases. We explain that how we can guarantee that our basis is in the bad shapes using the LWE method. We introduce the hard problem using LWE, which is the search version and decision version of the this problem. We explain the hardship of this computation. We again speak about the storage and computation cost of the LWE and how we can reduce it by using Ring-LWE method and again increasing the security by adding some other dimension to this computation, and then which is known as a modular learning with error here. Then we describe the encryption mechanism over LWE, and we defined the Alice and Bob computations during this key encapsulation mechanism. Both parties have some specific computations. They need to compute some things and then transmit it through the internet, and the other side will receive it and try to use it to encrypt the message, which is our shared secret key. Then we speak about how we can decrypt the message using these equations and obtain the message in the first side. We spoke about the dimension of our matrix here, our matrices and vectors here, and then we have the Sage example code that you can use it to overview the computation in our Kyber crypto system. And then we have some modification here for ignoring the this yellow value, this little value here. We need to round our result to 1 and 0 based on this value. If this value is more than half of the Q, we round it to the 1. If it's less than the Q, we round it to the 0. So we can compute the shared secret key here, which will be one of your question in your exam. And we know that for only actually 1-bit encryption and decryption, we actually study the cost of the computation here. So we compared the parameters for the Kyber from different perspectives, from actually the dimension of the key and the size of the secret key, public key, and ciphertexts for different security levels. And then at the end, we actually compared the computation cost of the some pre-quantums, actually pre-quantum approach, such as the RSA and ECC, with the post-quantum approach, i.e., I mean actually Kyber, and we compared them from actually the computation cost and the size of their key and the cost of actually the transmission of this number, this actually keys. And that's it. If you have any problem, my email address actually is mentioned in the first slide. You can ask me, and I will try to answer you if I can't. If I can't, I try actually to search it and see it. That's it. Thank you for your consideration.
Mushtaba, thank you very much. It was very good talk, very informative. I would like to thanks once again for your help putting together very well-written codes and explanation. So make sure that you have uploaded your or send me the latest version of your slides so I can have that available for the students. Students, if you don't have any question, or if you have any questions, you can always send an email to me, and also you can contact also Mushtaba. With that, I think we should be good. We're good to go. So thank you, Mushtaba.
Thank you. Thank you. Have a great day.
Bye.